Thanks for attending. We are in the next hour or so going to have a look at the new, and it is brand new, never been its own standalone part of the building regulations before. The new Part O that's looking at overheating in new residential buildings. If you've not come across us before, and I suspect some of you may well have been on the sort of Parts LNF versions of this that we did, that we've done previously. We are essentially our energy and sustainability specialists, so we do everything from SAPs, for extensions, SAPs for new build, all the way up to passive house consultants. We've just had a scheme finish recently that's just received its passive house certification that we did all the consultancy and the calcs for. Energy modelling of buildings, dynamic thermal modelling for various different overheating standards, whether it's BB 101 schools or TM59 and TM52 commercial and residential buildings. But that's essentially where that's our background. That's what the vast majority of what we do is. Hence why we come at this seminar, because this is pretty much our sort of bread and butter of technical competency. So what we'll do is we'll have a look at this new Part O. So this came into force on the 15th of June. So anything that was submitted for building regulations prior to the 15th of June technically falls under the old regulations. It does fall under the old regs, but there was no Part O, so Part O doesn't apply. So essentially it only applies potentially to projects that were registered with building control post 15th of June this year. And we'll have a look at what's involved in it. So there's the what's actually in Part L, the simplified approach to compliance, the non-simplified approach, which is full dynamic thermal modelling, and then what the transition arrangements are at the end. And obviously this is fairly topical, really, isn't it? This year we've had record-breaking summer temperatures, which is probably something that's only going to continue to go in one direction in terms of climate change and the impact that has on our climate. And what we really the aim of Part O really is to try and make sure that overheating is considered as a holistic part of the building design, so that what we're not having to do is we're not having to resort to slightly dubious approaches to overheating mitigation, as we can see in that in that image. We want the actual designed in building to avoid overheating without us having to resort to these sort of slightly Heath Robinson solutions. So that's where this is coming from, really. So what does Part O actually require? So paragraph O of the building regulation says that we must make reasonable provision in respect of a dwelling, institution or any other building containing one or more rooms for residential purposes other than a room in a hotel, to do two things. We have to limit unwanted solar gains in summer, so we've got to stop heat getting into the building. So obviously reference that previous picture where we've attached a slightly dubious looking awning over a window to provide some shading of that window. That's the aim of that, is to limit those unwanted solar gains. And then we have to provide an adequate means to remove heat from the indoor environment. So any heat that does get into our building, we have to make sure that can get out again. And in meeting the obligations in paragraph 1, we have to make sure that we have taken account of the safety of any occupant and the reasonable enjoyment of their residence. So our overheating strategy must enable the occupants of any buildings to be safe within that building, and to make sure that it doesn't create too much noise, pollution and things like that. And we can only use mechanical cooling as a means to remove heat if we have exhausted all passive means first. So we can't just go, oh, this is dead easy, we'll provide adequate means to remove heat from the indoor environment, whack a massive air conditioning unit on the roof. That is literally our last resort. So we've got to exhaust all of our passive means first, and then only then, if we have an unmitigatable residual overheating risk, then we can get rid of that with the use of mechanical cooling. So as a result, as we can see, this applies effectively to actually met several different types of building. It's not just relating to new dwellings. It relates to all new residential buildings. But does slightly sort of cut across the sort of Part L categories of residential and commercial, because you can get commercial buildings, which are things like student accommodation, sheltered living accommodation, HMO, boarding house. But they're all buildings that people are resident in for long periods of time. And in that case, for those types of buildings, they do fall under the remit of Part O. So it's not just dwellings, but it's also not relevant to all different types of commercial buildings. So, for example, offices, warehouses, they all fall outside of the scope of Part O. We don't have to worry about it. Schools as well don't actually fall in or fall under the remit of Part O. It's only looking at residential buildings at the moment. There are the two approaches: the simplified route to compliance and the DSM. They are very different means of doing it. The simplified one is very simplified. Is very prescriptive, as we'll see. And just a little bit of a note on terminology: when we look at the simplified approach, it does refer quite a lot to glazed area. And the glazed area is literally just that: it's the area of glass within the building. So if we have a window, it's not the structural opening, because it doesn't include the frame, because the frame's opaque. We don't get solar gain through the frame. It is literally the area of glass within any openings within the building, which allow light to travel through them. So I mentioned as well, or some of the criteria that we have to do is obviously we have to make sure that we're protecting the occupants of these buildings' safety, and also that we are ensuring that they can enjoy the amenity of their residence. So when we're coming up with our overheating strategy, we have to make sure that it takes into account a number of different things. Some of the main ones are noise. So, for example, if environmental health at planning stage have raised concerns about noise, whether that's from neighbouring roads, buildings, whatever it is, or there have been conditions if they're therefore placed on opening windows from a noise perspective, then we have to take account of that. So, if we're required effectively to have windows on certain elevations that are non-openable, then obviously our overheating strategy cannot assume that those windows will be opened to try and mitigate overheating. We have to make sure that it takes into account pollution. So again, if we have a scheme that's on a busy main road, and we are expecting to get air pollution coming off the vehicle, from the vehicles and their emissions from the road, then again, relying on openable windows on that facade may not be an appropriate means of ventilating the building and mitigating overheating. We have to make sure that if we're relying on opening windows or opening elements of our building, that we're not therefore creating a security risk. So ground floor windows, for example, therefore can be difficult, to rely on those being openable, particularly French windows and doors on the ground floor. Those are, I can't imagine there'd be too many people who would be, comfortable with leaving their, French windows open overnight as a means of mitigating overheating. So again, if we are going to end up being reliant on opening ground floor windows or windows in non-occupied rooms within a within a building, we may need then to provide some kind of security device to stop ingress into those spaces. We have to make sure that people can't fall out of any openings. So if we're high-rise flats, for example, we may need to either put limitations on the angle that windows can open to, which may therefore mean that we need larger areas of opening windows, but we need to make sure people can't fall out of anything, and that if we do have controls either for the security systems or anything else, that people can't get stuck in anything as well. So I don't, for the last two, I don't think there's anything in those that's anything over and above the requirements of approved document K. So I don't believe there's anything in there that is a particular, problem in that regard. But we do have to consider those, as issues as part of our overheating strategy. So what is in the simplified method? The simplified method is, it is very, very, very simple, really. We basically look at two things. We look at whereabouts our development is within England, to see whether it's in an area of the country that is at high risk or moderate risk of overheating. And we look at whether or not the individual unit, because it is unit dependent. If we have a big block of flats, we're not assessing the block as a whole. We are actually assessing each distinct residential unit within that building. We also have to look and then see if those units are cross ventilated. So we may have, depending on the layout and design of the building, we may have some units that are cross ventilated and some that aren't. So different criteria may apply to different parts of the same building, depending on the design and the layout of it. But in terms of risk, it's very simple. Basically, if we're in central London, we're in a high risk area. If we're not in central London, we're in a moderate risk area. That map on the right hand side does show us, the extent of all high risk areas across the whole of England. So, a building that's in Newcastle will have, according to this, the same moderate risk of overheating as one that's on the Lizard, for example. So, simplified approach. This is more to do with the urban heat island effect, really, and it's not really to do with location within the country per se. It's more to do with the built-up nature of central London and the fact that it's a very well-known situation that temperatures in central London tend to be significantly higher than those in the surrounding area, even for the same, weather conditions. And what we do is, once we've established whether our building is at high or moderate risk of overheating, whether it's cross ventilatable or not, I should say cross ventilation is openings on opposite facades. It's not just dual aspect. So a corner flat, for example, that wouldn't be cross ventilated because the openings are not on opposite facades. But we look at that, and then there are some tables within the approved document, and they tell us exactly for sort of criterion 1, which was ingress of heat or limiting unwanted solar gain. These tables tell us the maximum extent of glazing that we are allowed within our individual units. So let's say we were looking to build a block of flats in Nottingham. Nottingham obviously is not in central London, so it is therefore at a moderate risk of overheating. And if our flats are not dual aspect, they're all effectively, they're not cross ventilatable. So whether they're single or, corner flats doesn't really matter, but they're not able to be cross ventilated. So we're using this table at the bottom. So limiting solar gains to buildings without cross ventilation, we're in a moderate risk location. And so what we can see is that depending on which orientation the majority of the glazing faces, we're limited basically to this amount of glass as a proportion of the floor area. So the more of it we face in the orientations that are likely to give us higher solar gain, the less glazing that we're allowed, basically, the less glass that we're allowed. We are allowed a little bit of leeway potentially, to put more glass in one room. So, for example, in our flat, if we wanted to have a large French window in the living room, we can have that for certain orientations. We're allowed to have a little bit more glazing in some of those areas. But as I say, this does, give you quite a restrictive approach to the fenestration design of a building, because it is very, very concerned with restricting the amount of glazing. As we'll come on to when we have a look at a couple of case studies, this is actually slightly more. This feels more onerous than it is actually potentially for the glazing, and we'll see why I say that in a bit. if we are building in a high risk location, so if we are building something in those areas of central London, then we have to provide shading for any glazed areas between northeast and northwest via south. So any glass that doesn't face pretty much due north, we've got to provide a means of shading on that. And that is why, actually, interestingly, you find that some of these high risk locations, you're allowed more glazing than you are with some in moderate risk locations. And that is literally just because these ones have to be shaded in a high risk location, whereas the ones at a moderate risk don't have to be shaded. So if you shade your openings, you can have more of them because you don't get so much solar gain through them because they're shaded. But shading means one of three things. Well, there's three approaches that we're allowed via the simplified approach. We either have to have external shutters with a means of ventilation, so louvered shutters, glazing with a maximum G value of 0.4 and a light transmittance value of 0.7. So it has to cut out unwanted radiation with that G value of 4, but it still has to let enough light through that we still get amenity daylighting in the space. I think double glazing is about standard double glazing, even with a low E coating, comes in about 0.6 on the G value. Again, I think standard triple glazing with low E coating comes at about 0.5. So glazing with a maximum G value of 0.4, we are looking at something that does have an additional solar film coating on the outside face. We're not going to achieve that with a standard window. And the last thing we could do is on any south facing facades, we could have an overhang with a 50-degree altitude cutoff. So brise soleil, balconies above, whatever it is, it just has to cut the sun out when it's above 50 degrees from the horizontal. So that's our example of our 50-degree altitude cutoff. Has to stick out far enough at a 50-degree angle is subtended by it. We do provide external glaze shading, then SA has to have a means of ventilation. So a blind like that is not sort of compliant with those simplified approach criteria. It would need to be something that's louvered. So the idea behind this is that we can cover the window up with it, but we can then still potentially open the window behind it and get airflow through the building, depending on our requirements. We're not with this approach, we don't get solar gain, but we also, whilst this is down, we get no there's no ability to get ventilation through that opening. We also need to provide a means to remove excess heat from the building. And again, in the simplified approach, this is set by looking at a couple of tables, basically. So for our block of flats in Nottingham, which is therefore moderate risk without cross ventilation, we look at the table at the bottom. This gives us a total minimum free area. So essentially, we are reliant in the simplified approach on opening windows. That's our means of getting heat out of the building, is having openable windows. And for the moderate risk location, we have to have the greater of the following: 12% of the floor area or 80% of the glazing area, whichever of those is the greater. And so obviously for the high risk, it's slightly different. And again, criteria up here, they're different criteria, but we just look at the table and select whichever one of these are appropriate for our development. We also have to have a minimum of 4% of the floor area of the room in bedrooms as well. So the free area, we can get that either from product manufacturers. They may well have, so the window suppliers may well have that data. There are a series of tables in the back of the appendix, Appendix D to approved document O, which gives you free areas for a range of opening sizes and opening angles. So we can find the information from there. And if we follow, or if we provide the openings that are mandated by the simplified approach in ADO, then we will meet the Part F purge ventilation requirements by default. However, meeting the Part F purge vent will not give you sufficient opening area to meet the Part O requirements. So it will require openings over and above the areas required by by Part F. So as you can see, if we can't use opening windows, then we're going to struggle to use the simplified approach at all. And then we may be forced onto the DSM approach. We also can't use the simplified approach if we have any form of communal heating system within the building that's circulating heat via pipework running up and down corridors. So if we have horizontal distribution through corridors from a district heating or communal heating system, then because of the heat gains we get in those corridors, we can't use the simplified approach at all. So we'll have a look at a couple of case studies of how we actually apply the simplified approach sort of in practice. So here we've got 4 identical townhouses. These are in, where are these? Bracknell. These are on the outskirts of Bracknell. So they're not in a high risk area because they're not in central London. They're in a moderate risk area. And as you can see, fairly standardish looking, you know, townhouses really. And actually, you'd look at these and you don't think there's, you know, sort of a shortage of glazing on these. They don't look underglazed. They look like they've got a reasonable amount of you know, openings both on the front and the rear elevations. But actually, as we can see, the site faces east-west. Largest glazed area actually faces east. That's the rear elevations because they've got those French windows on. We calculate we measure the total floor area, gross internal area, and then we measure the glazed area of the most glazed orientation. Sorry, we actually measure the overall glazing. So we measure the area of glass in all those windows. Now the thing about these windows obviously is these are a mock sash, you know, style window, and so there's actually quite a large amount of the structural opening area that's taken up with frame, with glazing bars, you know, and so actually they look like they've got a reasonable area, these windows, but there's actually not as much glass in them as you might think. And so that's why we actually have, in terms of glazed area to floor area, we're only at about 10%, which is well under, because we're in a moderate risk location. We are therefore well under the 18% that we are allowed for an east facing most glazed orientation. And in fact, we could actually flip these houses around if we wanted to put them on a, you know, if we had a bigger site with the same house type, we could flip that house type for 180 degrees, face that larger glazed area west, and we would still be below that, you know, below that requirement. Particularly because, again, even our maximum area of glazing in the most glazed room, which again is the living dining room on the ground floor, because that's got the French windows in. So we've got French windows and another window over here. Even there, we're still only at 12% of that room. So actually, potentially, it's not as restrictive as we might think if we're looking at houses when it comes to the simplified approach. What we tend to find actually is that the limiting factor tends to be the opening area of the windows. So the way that this scheme's been drawn up, as per the drawings, are that we've effectively got top hung mock sash windows. So it's only the top half of each window that's actually openable. They can only open to about 30 degrees. And we have therefore taken the free areas for these windows from the tables in the back of the approved document, because this is a pre-planning stage that we've been looking at this, and so obviously they don't have a specific window supplier in mind, so we can't go to a window manufacturer to get that data because we don't know that, you know, their products will be the ones that are actually used. So we just use the generic data from the back of ADO. What this actually shows is that in total, we've actually only got about 5% free area versus floor area, and compared to the overall glazing area, it's only 48% rather than the required 55. So for this particular orientation building, we're not actually we don't have, the windows don't open sufficiently to give us enough free area to get that heat out of the building again. We've got small enough window, small enough area of glass, even that it's not that it's you know, we're not going to get too much solar gain, but that solar gain at the moment can't be got out of the building when it's slightly cooler overnight. The bedrooms are all compliant, actually, and so what this really tells us is that because a large proportion of that glass is tied up in those French doors on the ground floor, we can't rely on those French doors as being openable, because what we're doing then is we're essentially saying, oh, just leave this door on your ground floor open overnight, you'll be fine. Don't think that's really appropriate, and I can't see too many people wanting to do that to mitigate their overheating risk. And so as a result, those doors are closed. That's a significant free area. It's also a significant area of glass that we're not able, therefore, to have an opening area with. So what we'd essentially have to do with this is we would then need to go and re-look at the design of the windows and say, well, okay, do we have to have the Moxash style window? If we do, actually, can we come up with a design, or can we select a window product that gives us a greater free area? Now, that may be actually using rather than having a top hung Moxash, well, actually, it doesn't mean that we have to go to a full sash design, so that essentially half the window has a massive free area, because we can lift it up and we have that complete area. It's completely free, and that would give us a very large free area rather than being restricted with a top hung or casement that only opens to sort of 30 degrees. So that's what we'd be looking at in this case, is basically saying, well, okay, on those windows that are on the upper floors, we need to get a greater free area out of those. So we would then need to look at changing that fenestration design to get those greater opening areas. As a slightly different example here, we've got quite a big self-build style dwelling. So as you can see, we've got massive open plan area. You can see from here we've got these big areas of bifold doors on the back. We've got big double height space here over the dining room. More large areas of windows on this rear elevation. And as we can see, helpfully, all this massive areas of glass, all faces basically bang on due south. And if we look at the elevations, we can really see, from the front, it's a fairly traditional, in inverted commas, style building. But when we look at it from the back, we have some enormous areas of glass. This elevation looks to be to have a very significant proportion of its external area as glass. But actually, interestingly, if we look at this overall, so our largest area of glass faces south. We know this, it's not in central London. So again, it's in a moderate risk location. We're around 15% overall, 30% in the most glazed room, which obviously is that big open plan living kitchen diner. But actually overall, we're only at 15.67. So we're not actually, even though we do have what appears to be a massive area of glass on that rear elevation, we are not that far over the target. And essentially that's really because actually, if we look at the other elevations, I mean, there's basically nothing on that elevation at all. We look at the elevations and they are not, they do not have significant proportions of glazing on them. And so although the majority of it has been concentrated onto that south elevation, we're not actually that far off. We could probably trim this. We need to do something on here, because as we can see, we're also over the threshold for the largest room. So we do need to do something about trimming, or potentially, if we want to use the simplified approach anyway, we need to provide something that will trim that area of glazing back. But we're not actually as far away from these simplified criteria as we we might think just from looking at the drawings. Which is why I sort of said earlier, really, that actually the simplified approach is not quite as restrictive as you'd think when you look at, those areas in the tables. You look at those and you immediately think they are incredibly restrictive. It's not necessarily the case. I mean, these are helped by the fact they've got a very big floor area. So obviously, if you have a massive floor area, 15% of that, it becomes quite a big area of glass that you're allowed. You know, but it's not as bad as you might think. But again, where this suffers is very significantly on the areas of on the free area of openings, because again, we can't open those two massive bifold doors on the ground floor. We can't leave those open overnight, you know, because they would be a significant security risk if we left those open. If we go back, we can see that there are a significant areas of, you know, fixed glass that can't be opened. So all of these, all these windows up here, they're all fixed. They can't be opened. These top lights over here can't be opened. And this one over here, it's only this central door that can be opened over there. So even though these doors could be left open overnight because they're, you know, potentially in an occupied bedroom, but they're also on the first floor, so they're unlikely to cause a major security risk overnight. You know, we can't leave those. We do have large areas here that are not actually openable, and so when we look at those criteria, we have to provide 9% for it. We're miles off it. Yeah, and again, if we look at it on the glazing area approach, we're an awfully long way away. And again, that's been able to do with the areas that are openable in terms of the design, but also in terms of what we are allowed to model as open when it comes to ensuring the security and people's reasonable enjoyment of their residence. So yeah, so, you know, bedrooms tend to be all right. Again, you know, in terms of those criteria, bedroom 4's got a massive door. That's why it's got a ridiculously high, you know, proportion. It's got a wacky great French doors that can be opened. You know, so you know, even the bedrooms at the front where we've just got, you know, these two casements either side are openable to 40 degrees, they still give us plenty of, you know, plenty of free area. But again, it's looking at it overall, we can see there's large areas of glazing that can't be opened. It all faces south. So essentially, the simplified approach kind of confirms roughly what you'd expect looking at the drawings in this case. You know, you look at that and you'd say, well, I know which areas of the building are likely to overheat, the ones with all the glass in it faces south. And that's really what this is confirming. You know, we need to do something about the glazing in that space. So we could either dramatically revise the design and completely change the fenestration, which we'd have to do to comply with the simplified approach, or we could potentially push this on and say, well, okay, actually, how can we make this glazing work if we want to use, if we're trying to make this design work, we then have to drop onto the full DSM approach, model it in that approach. And what we could do then is we can start to look at potential mitigation options. You know, so we could look at blinds, for example, or, you know, movable awnings for those big bifold doors, which would give a large amount of shading over those, which would, you know, massively help. You know, we can say, well, okay, that's a big double height space. We know that's likely to overheat. Let's put some opening, you know, some automatic opening lights in the roof, because that's, you know, open all the way up to the bridge in that area. Let's put some opening roof lights in, so we can keep those fixed areas, but actually we know that we can expect the heat just through the stack effect to actually purge itself out of that space. What would the impact of that be? We can model that using DSM, because that models the airflow through the building and through all the different openings. So if you want to keep that fenestration design and we can't get it to comply with the simplified approach, that's one of the routes that we're looking at. You know, that we've then be looking at the full DSM approach to say, well, okay, can we now come up with some options? You know, what can we do to this space to make sure that it doesn't overheat? But in terms of looking at it from the lens of the simplified approach, that doesn't comply, and we would need to dramatically revise the fenestration design to get that to comply. So as I say, that really is what brings us into looking at DSM. So the aim of the DSM approach is to give us more flexibility with regards to the design, for those buildings that don't necessarily fit the simplified approach. So to a large extent, the simplified approach has been designed to work for, developers who have a range of standardized house types. They can resize all the windows in their standard house types, and they know whether a house type will comply before they stick it on a drawing. A site layout plan. It's not necessarily going to work for all schemes. So if either we're looking at buildings which are incredibly airtight and incredibly well insulated, then the simplified approach may not be applicable. We can't open windows. So if we have site conditions that mean that the plan or environmental health said no, it's going to be far too noisy, to mitigate that noise risk from that particular source over there, all those windows on that facade will have to be non-openable. Then again, we can't be simplified because we can't open the windows. Or if we've got a building that we do want to have those large areas of glass and we want to keep those, we don't want to be restricted by that simplified approach. That's when we need to look at doing the full DSM. And essentially what this is running an analysis of the building following CIBSE's TM59, but with a set of occupancy criteria that are defined within ADO. So there's a range of occupancy criteria that are a little bit different to those that you can use if you're just doing the standard TM59, but it's the same TM59 methodology. But what this approach allows us to do is it does allow us to consider every single aspect of the building design. So we're not just looking, well, okay, this has got X area of glass, is that greater than the threshold? Can we open the windows? We can we can shade those windows using any form of shading we like, whether that's say a dynamic approach, i.e. something which automatically opens and closes, or a blind that automatically drops if the sunlight exceeds a certain threshold on a sensor. We can look at overhangs. We could whether that's whether that's an eaves overhang, whether that's a purpose-designed brise-soleil, whether it's undercutting the ground floor back and having an oversailing first floor, whatever it is. Size and orientation of glazing, obviously. G value of the glass makes a difference. Reveal depths can make a surprising difference. The bigger the external reveal depth, that actually provides shading across to windows. Building orientation and its positioning in relation to adjacent buildings as well. So again, if we're doing the DSM approach, we will model any surrounding buildings. We don't tend to model external surrounding trees, but you would model any surrounding buildings, because those may well have an impact. If they shade certain windows at certain times of day, then obviously that provides benefit to those windows in terms of mitigating solar gain. We can also articulate the facade of the building as well. So if we wanted to have our if we had some setbacks within the building facade, those then had some balconies in, then obviously any glazing that we put in those setbacks actually is automatically shaded, not just by the setback, but it can also be shaded by the balcony above. So that can be quite a good way of getting some passive gain as well, in terms of protecting windows. So TM59 has some it also actually allows us to take into account significantly wider range of means of getting heat out of a building. We're not just restricted to opening windows. We can put louvres in different designs. We can model the impact that those have. We can model the impact of mechanical ventilation. And again, as an absolute last resort, we can then potentially look at mechanical cooling, but we do have to exhaust those earlier steps of the cooling hierarchy even first. So what does TM59 actually require? So these are interesting things to try and define in some ways. They're not necessarily the most simple ways of doing things. There's two basic approaches. There's an approach for naturally ventilated homes, and a naturally ventilated home, for the perspective of TM59, is defined as one that you can open the windows in. It may still have MVHR or some form of mechanical ventilation system, but if you can open the windows in it, then 1059 would class that as being naturally ventilated. And there are two criteria that we have to achieve for a naturally ventilated home. The first one is what's called delta T. And this is that for living rooms, kitchens and bedrooms, so the habitable rooms within the building, the number of hours that delta T is greater than 1 degree between May to September is not more than 3% of occupied hours of the space. Delta T is an interesting metric in a way because it's not a fixed value, actually. But it's the difference between the operative temperature in the room and the limiting maximum acceptable temperature. And the limiting maximum acceptable temperature is 3 degrees above the comfort temperature. So, as I say, could go into how each one of those is calculated, but it's kind of not that easy because it does actually vary. It's not fixed. But that's what we're looking at. So delta T effectively is a measure of the hours that we're exceeding a set comfortable temperature for a space between May to September. And that's applicable kitchens, bedrooms, living rooms, so habitable rooms. We then have another criteria that's relevant only for bedrooms. And that essentially is that the operative temperature shouldn't be more than 26 degrees, more than 1% of the occupied hours overnight. So this essentially is, how comfortable are the bedrooms for people to sleep in overnight? And essentially, if we're more than 33 or more hours above 26 degrees, then that's a fail. If we have a building that is actually primarily mechanically ventilated, so we can't open the windows in it, it actually makes things much easier. There is then only one criteria that all rooms need to apply, and that is that the occupied rooms should not exceed 26 degrees more than 3% of the annual occupied hours. That's therefore pretty easy. That's just that one criteria. It's a fixed value. We can't be above for 26 degrees for too long. We do have to consider a few additional things. Probably the most relevant, or the one that has the biggest impact actually, is whether or not we have any vulnerable occupants. So if we were looking at, something for, say, sheltered, sheltered living or a care home, where we've got vulnerable people, it effectively makes the delta T target harder to achieve, because rather than it being 3 degrees above the comfort temperature, delta T then becomes 1 degree above the comfort temperature, which obviously is less of a leeway. We can't have as much gain in that space because our target's lower. But that's the one that has the most impact. We don't necessarily have to consider every single unit on a site. We can, for the purposes of 1059, we just have to consider a representative sample. So we could do the worst case of each house type, for example. We don't have to do every single flat in a block. Potentially we could just model the ones that are on the, the riskiest facade. So, we don't necessarily have to model everything. If we're doing DSM, we can just pick on a sample across the site. And if we do, again, if we have a building that has communal heating, so we've got heating pipe working corridors, then we do have to model a selection of those corridors, because we do get gain from those. We can't therefore use the simplified approach. We have to assess what the temperature is going to be in those corridors to make sure the corridors themselves don't overheat. So a little bit of a case study. This was actually done for London Plan purposes, this one. So this is pure 1059. It's not technically Part O, but it's 1059. So it's the same approach. So it's a good example to have a look at. So here we've got essentially a was it 4 or 5 story, I think, block, 40 flats, I think, in here. So we've got a little bit of commercial space on the ground floor. That's obviously exempt because that's expected to be retail. So that's not residential, doesn't fall under the remit of Part O. So we're not bothered from a Part O perspective whether this overheats. Got one ground floor flat that is, that is cross ventilatable there. And in fact, as we go up, you'll see all the ones in this core of the building are all able to be cross ventilated because we've got opening windows here, and also then opening windows on this facade over there. North is the top of the drawings on here. That's north. South is down here. As you can see, as we go up the building, You've essentially got 4 flats of floor, one there, one there, one there, and then this one over here. We work our way all the way up, and then we hit a bit of a penthouse area at the top here. As you can see, we've actually got some nice articulation of the facade on here. We've got these nice recesses. These areas of balconies. They're all recessed into the facade. Obviously, each one's got a balcony above. So again, these areas then effectively become sort of, self-contained. They're nicely shaded. Both by the projections on the sides and as well as the balcony that's set over the top. So there we've got our recessed elements, and as you can see, even the roof oversails the top of those as well. So even these ones that are, say, on the top floor, kind of, if they have a roof over the top, those still have that same shading as the ones on the lower floors. And so what we've got here, you can see this is our full model. And so as you can see, all the surrounding buildings, even the ones across the roads, they've all been modelled and built in as well, so that we can, model the impact they may have on the shading of some of these openings. They're all given different characteristics depending on the window. So as you can see, we've got, some of these are tilt and turn. Fully openable windows. We've got some doors over here. They've then got elements next to them which are top hung. Red ones are all tend to be fixed. Well, they are all fixed panels. They're all closed windows that can't be opened. And we potentially, these then all have their relevant characteristics applied to them. So we can say what the free area is. And then the software then can model the movement of air through those spaces as part of the calculation. And so what we actually find with this is that the problem areas that we have are actually effectively 6 bedrooms and 5 living rooms. And effectively they are, to start with, we've got 1.3, 2.3, 3.3. That's these ones here in the corner. And as you can see, effectively that's because we have a living room here with fixed windows both on the south and the east elevations. As we can see there, these ones over here, they are quite fixed. They're only small proportions that can actually be opened. And then basically everything on this top floor, because we've got no shading at all. There's no shading over the top of any of these openings. And so these are all showing, that we are running at above 26 degrees for excessively large amounts of time, basically. That's our delta T criteria. Some of them fail the delta T criteria, which are all the living rooms, and then it's the bedrooms, obviously, then that are failing that total hours less than 26, or sorry, more than 26 degrees. So what we've done then is we've gone back and said, well, okay, then we need, we need to look at this. So the architects come back, tweak the fenestration of the building slightly, give us a few more openable areas, although they're not that big. They're actually these ones here and these ones here, so they've not really added a huge area. That's mitigated, obviously, some of the issues in those rooms, but obviously the areas that were failing, where they've not actually been able to add that extra opening areas in, are still failing. And so what we've essentially had to do then is to mitigate that risk. We've had to add a mechanical ventilation system in that's going to give us 4 air changes per hour in those spaces. So that's something which the M&E designer is going to have to consider, how they can deliver those volumes of air, whilst maintaining the acoustic, standards within those spaces. But it does mean, that we can, if we can't mitigate it passively in terms of building design, we can then take the next step down on the energy hierarchy, which is mechanical ventilation. We're not doing any cooling at this point. We're just using mechanical ventilation to give us an additional air changes per hour. There's no mechanical cooling involved in that process at this point in time. So we've still managed to, although we've moved down the hierarchy, we've not hit that bottom step, which is the mechanical cooling. Once we've got our design fixed, so we decided whether we're doing simplified or DSM, whatever it is, we've worked out what our design actually is. We then need to provide, as part of the handover to the owner of the building, we need to provide a document to them that details our strategy. So we need to cover what it is, how it works, when you need to use certain things within the building, how those are controlled, how they're maintained, all those things. It's basically O&M manual specific to overheating. So if you're doing a commercial building that fell under Part O, you'd probably just plug this into the building logbook or the O&M manual. If you're doing a dwelling, you'd find this would form part of the new home use guide. And there are some sample report templates that can be used. So again, these are detailed in the back of the approved document. This is the simplified approach one. It's fun enough, quite short, but again, essentially just requires whoever's done the check or the design to say whether it passes or fails, and then for them to put their name against it as whether it does comply with Part O or not. And then again, we have the same thing for the DSM. Obviously more complicated because DSM is a more complicated process, much wider range of variables we have to document. But again, it's still got the same approach. So we then have whoever's done the modelling. In this instance, would say, has it been modelled accurately? Yes or no. Don't know why on earth you'd ever select no, but maybe. But essentially, you're then expecting whoever it is who's checking that against the criteria to effectively put their name against compliance. So the last thing to note are transition arrangements. So any project that was registered with building control prior to 15th of June this year, Part O doesn't apply. However, it only doesn't apply if you start work on that project and on the individual buildings on that project within 12 months. So if you've not started on something by 15th of June next year, that building will actually fall under Part O. So even if you've had a site that's a project that's been on site for 2 years, as of now, if you're building out a range of houses across that, anything that you've not started on by 15th of June next year would fall under Part O, and that would apply to any of those plots that hadn't been started. So there are transitional arrangements in play. However, they are not site-wide anymore. They don't lock the whole site in. They only lock the individual buildings upon which work has been started. So there we go. Hopefully that's kind of a useful look at Part O, what's involved, a few case studies that show how we can get compliance, whether it's following the simplified approach or the DSM approach. Has anybody got any questions? Feel free to unmute yourselves or bash away in the chat.
I've got one question.
Yep.
The shading from adjoining buildings, I understand why it's taken into account, but how can you be sure that those buildings are going to be there for any length of time?
Yeah, I mean that's a good question. I think to some extent you would take that view when you're modelling it. I think you would just assume that they are going to be there for a long time, unless you've got any good evidence to the contrary, if that makes sense. So if it's a derelict building next door, you might decide that actually you're not going to model that one. But yeah, I think if it's a building in good condition and it's occupied, you're likely to assume that it will be there for a decent period of time. But yeah, there isn't any guarantee, and so potentially you could just model everything without those neighbouring buildings if you were concerned about it.
Thank you.
That's right. So someone's put in the chat, do trickle vents have any relevance here? So in the simplified approach, no, they're not considered. Their impact is not considered as part of the simplified approach. If you were doing the DSM approach, you can model the effect of trickle vents. So you you effectively would build a ventilation slot in the building above any windows that had a trickle vent of the correct size. And so yes, you can model the effect of trickle vents on buildings as part of the DSM approach, but as part of the simplified approach, no. My suspicion is they're probably already taken account of, but no, they don't give you any mitigation over the simplified approach criteria.
Sorry, I was just looking at some of the notes I've made. The value of the glass, thermal performance of the glass, how much is that influence? The solar gain, reflection, or whatever. I know it doesn't overcome ventilation if you use it in large areas, but is it quite influential in the calculations if you pay for the right glass?
The G value can be, yes. Yeah. So you can get some, you can get sort of, again, you'd be looking at, you would only be able to reflect that by modeling that via the DSM approach. The simplified approach basically doesn't take account of the G value of the glass. There's just a requirement that it's below a certain value if you're in a highly, if you're in a high risk area. But anywhere else in the country, the G value doesn't make a difference to that simplified approach. So if you did want a large area of glazing and you wanted to justify it by putting a solar film on the outside, and you can get some pretty impressive solar films these days that do have quite a low G value, but also have a decent light transmittance value. So they're not just black glass. Then you can model those in the DSM approach, and they can have quite a powerful impact on it. Yes.
Okay, thanks.
That's right.
I missed the beginning, so I didn't work out whether it applies just to new build or if it applies to just retrofit replacement windows.
No, this so the Part O applies to new residential buildings only. So it doesn't apply to conversions, it doesn't apply to any existing buildings, and it doesn't apply to any extensions. So you could build a glass cube on the back of your house, that would be a highly glazed extension under Part L, but that wouldn't trigger a Part O assessment because it's part of an existing building.
Thank you.
That's right. If you missed the start, we have actually recorded the whole webinar. So when we send you a PDF, you'll get a PDF of the slides and a CPD certificate emailed round. We'll also send you a link to the whole thing. So if you missed any of it, you can always go back to and watch the recording if that's of any help. Cool. Right. If nobody else has got any questions, then obviously thanks for thanks for coming. As I mentioned, we will get a PDF of the slides, we'll get a CPD certificate and a link to the recording sent round to everybody who's been here. By all means, send if you've got any colleagues or anybody that who you think would benefit from it, you can always forward the recording link on to them. This is, fun enough, something that we're seeing an awful lot of inquiries about at the moment because it's quite topical with the year that with the summer that we've had. But also to an extent, it's probably quite a key thing to get sorted out on projects, preferably at an early stage before changing the fenestration design becomes a problem. So if you've got any questions or anything on any specific projects, then by all means let us know. Otherwise, thanks everybody for coming, and I will and have a good rest of the day.